to power electric vehicles for longer distances, and keep smartphones and laptops charged at all times. The core element of batteries is indispensable: lithium. Approximately 70% of global lithium resources are found in salt lakes. However, extracting lithium from these brines poses significant challenges: low lithium ion concentrations, and contamination by impurities like boron and magnesium. How to solve this problem? This episode introduces bipolar membrane electrodialysis and its role in enabling efficient lithium extraction. In subsequent episodes, we will explain how lithium-selective adsorbents capture lithium ions to yield a preliminary lithium-rich solution. However, this solution still faces two critical issues: residual impurity ions, lithium concentrations far below industrial production requirements. This is where bipolar membrane electrodialysis steps in. Let's talk about electrodialysis first. The system alternates cation and anion exchange membranes, separated by spacers, and flanked by electrode plates. The anion and cation exchange membranes in the membrane stack are alternately arranged to form dilution and concentration systems. After brine is introduced, under a direct electric field, lithium ions migrate and concentrate, achieving concentration, while separating boron from lithium, with a boron removal rate of over 90%. A bipolar membrane is composed of cation exchange layer, catalytic layer and anion exchange layer. The catalytic layer accelerates water dissociation into H and O. The anion membrane passes anions, and the cation membrane passes cations. The bipolar membrane electrodialysis system, formed by combining bipolar membranes with anion and cation exchange membranes, also has accessories such as spacers and electrode plates, etc. Under the drive of the electric field, by splitting water molecules, the bipolar membrane decomposes water molecules to produce hydrogen ions and hydroxide ions, which react with other ions. Without introducing external chemicals, it generates H and O ions to convert salts into acids and bases in situ. In practical applications, using brine from salt lakes as the initial raw material, lithium is extracted by adsorption method. To obtain a lithium-containing solution, the lithium-containing solution is passed through nanofiltration process to remove polyvalent ions. Then reverse osmosis technology is used for preliminary concentration. At this point, there are two different routes. Route 1. The pre-concentrated feed solution enters the electrodialysis system for further lithium concentration. Then the concentrated feed solution undergoes lithium precipitation reaction to finally obtain lithium carbonate products. Route 2. The pre-concentrated feed solutio enters the bipolar membrane electrodialysis device, where electrochemical reactions occur to produce hydrochloric acid and mixed alkali. The produced hydrochloric acid is used for lithium adsorbent regeneration and lithium precipitation and adsorption, so that the adsorbent can continue to be used in the lithium adsorption process. The alkali liquid in the mixed alkali undergoes a series of treatment processes such as evaporation, crystallization and drying, to finally produce battery-grade monohydrate lithium hydroxide products. Bipolar membrane electrodialysis technology has advantages such as targeted purification, impurity removal, self-supply of acid and alkali, low energy consumption, low temperature and low pressure operation, and high purity of prepared salts. In short, lithium extraction from salt lakes not only needs to rely on the high selectivity adsorption of lithium adsorbents for the preliminary separation of lithium ions, but also cannot do without electrodialysis and bipolar membrane electrodialysis technology for the concentration, purification, and transformation of solutions. The combination of the three can better utilize the lithium resources in salt lakes to meet the growing demand of the new energy industry for lithium resources.